Started. Hello, everyone. Thanks for joining the very first SNAPP seminar. As you all know, today we have Professor Bruce Hajek to kickstart this seminar series. Before we start, I just wanted to take a quick minute to thank our organizers who made this possible. So Devankar Mukherjee from Georgia Tech, Veena Wang from CMU, and Christina Lee from Cornell. And I also want to thank our advisory board. The advisory board has Professor Jose Blanchard from Stanford University, Lauren Masoulier from India, Kavita Ramanan from Brown University, and Devavrat Shah from MIT. I also want to thank Symmetric for their cooperation in running this seminar series. I guess all of you can see the instructions. Please mute your audio. Feel free to unmute your video if you like, so that the speaker can see a few faces when he talks. I'll keep monitoring the chat box in case there are any clarification questions. We'll have a quick 1 or 2 minute break somewhere midway through the seminar so that you can ask any quick questions, and we'll have a more elaborate question answer session at the end of the talk. This talk is being recorded and also live streamed on YouTube. So today we have Professor Bruce Hajek with us. I think Bruce doesn't need any introduction for this audience, but I'll take a minute to quickly introduce him. He is the Hove Chair in Engineering at University of Illinois Urbana-Champaign, and he's also the head of Electrical and Computer Engineering Department. Bruce has been at Illinois for over 30 years. He got his BS and MS from University of Illinois, and then he made a quick detour to University of California, Berkeley to get his PhD and returned to Illinois. His research interests are very broad, and they include communication networks, auction theory, stochastic analysis, combinatorial optimization, machine learning, information theory, and bioinformatics. He has won numerous awards and recognition. I'll not list all of them. I'll just mention a few. He served as editor-in-chief for IEEE Transactions on Information Theory and as president of the IEEE Information Theory Society. He received the IEEE Kobayashi Award for Computer Communication, ACM Sigmatrix Achievement Award, and he's also a member of the National Academy of Engineering. Today, he's going to talk to us about non-unique solutions in mean field games. So Bruce, over to you.
Yeah, let me hand this over to Bruce.
Okay, thank you. Let me, okay, good morning. Yeah, so I'd like to talk about non-unique solutions in mean field games. I'd like to thank the SNAPP organizers for the invitation, Christina, Devankar, Siva, and Lena. I have a screen background here, which is from IIT Bombay, and I see Vivek Borkar is on the line. And this work started when I was first visited IIT Bombay, and I somehow done a lot of it went there. So I think it's fitting to have that screen background. This subject started about 15, 20 years ago, and it's been very active recently. There's a so-called partial differential equation approach, and it takes probably 3 or 4 hours to really get into it. So I plan today to give just an introduction and the simplest context. And this work is based, this talk is based on joint work with Michael Livesay. Michael got his PhD here at Illinois a year ago, and he's now working at Sandia National Labs. But this work was based on it. His PhD is in mathematics, but he did a master's in electrical engineering. And this is part of this is from his master's work. Okay, so I'm gonna switch to this iPad here. So first I'm gonna talk about the mean field game with one player. So it's just, if there's one player, it's not really it's a special case, but there's no one else that the player is playing against. If we understand well how it works with one player, then we can fall naturally into thinking about a game with many players, which each behave like the one player. And then I'll talk about fluid limit trajectories. So the theory of mean field games was initiated independently by Wang, Keynes, and Mallarmé, and Lazary and Lyon. And not too long after, Gomez, Moore, and Souza wrote a paper that translates much of what Lazary and Lyon's did into the case of finite state Markov processes. If you want to do anything very explicit in mean field games, you should start with some control problem where you have fairly explicit solutions. And one of those is the LQG setting, where you have very explicit solutions. And the other one is a finite state Markov processes. The theory of dynamic programming for Markov processes is fairly explicit. So I really like to have examples, and so I'm focusing on the finite state Markov process case. But a lot of the theory can be translated. The Lazary-Lyon one, they start out with Markov diffusions in a very general setting. So if you want to understand all the different theory.
Sorry, I missed that.
Sorry.
Could you say it again, please?
Okay, looks like my cell phone wants to get involved in this. Okay, see what happened. Can you see? Yeah, there we go. All right. Sorry, my screen is frozen, so. See, my iPad is frozen on this page. Let's see.
Do you want to stop sharing and restart again?
Maybe. Okay, I think this is, came back, so. I'm not sure what's going on. Let me try that one more time. Well, I can go to plan B. I can open up the PDF and just share from the PDF. So documents. Let's see, notability. Field game. That's not going to work either. I'm not sure what's. My laptop says froze, totally froze.
Sylvia, if you have the slides, maybe we can share, like you can share the slides and.
Right, yeah, so let me try sharing my, let's see, how about if I share my whole screen? That might be the safest one, so And view screen.
It's very small right now. Okay.
All right. So can you see my mouse here?
Yes.
All right. So it's not ideal, but okay. So one player game. So the simplest case of a controlled Markov process is probably a two-state Markov process where there's one player that's in state 0 or state 1, and there's some transition rate alpha 0 to go from state 0 to state 1, and a rate alpha 1 to go from state 1 to state 0. Okay, and you can think of this as a Q matrix, which has this form. It's a generator matrix. And then if we have some initial probability distribution, and if these rates they could be time varying, then we have the Kolmogorov-Ford equations, and we can calculate the probability distribution at any time t, starting from the initial distribution. So if the current state is I at time t, then we go to state I minus 1, the other state with probably alpha times h plus little o of h, and a period of length h. Okay, that's a rate. So there's the Ford-Kolmogorov equations, which was a differential equation that will give the probability distribution at time t. It's basically a fluid type equation. So pi of t is the probability of being in state I at time t. Then the probability leaves there at rate alpha, so you lose that probability, and the probability being the other state is this, and there's the rate that you jump from the other state increases the probability. So that's Kolmogorov-Ford equations, which I assume is familiar with everyone here. Okay, now we can also think of a control problem for a two-state Markov process. So this is a finite horizon control problem. I of t is a state at time t, which is controlled by a single player. Alpha of t is the rate that the player is trying to move to the other state. And there's some terminal cost. So if capital T is the state at the end of the time, there's some terminal cost. So the alpha t here is short for the control function alpha evaluated at the current state and at time t. I'm going to look at a particular case for the cost, which is a holding cost, or the cost for the player to be in state I at time t. That will be integrated there, plus alpha squared over 2, which is a cost for applying control. So the player might not be very happy with current state, but the player has to pay to make a transition to the other state, and the cost is the control, the rate squared over 2. Okay, so hopefully, so this is, to really get into the subject, it's really important to understand the very basic control problem just for one single player. And in any type of mean field game theory, you want to have a really solid understanding of that. And then the mean field game theory sort of naturally goes from there. So for a single player, dynamic programming works, although this is continuous time. We look at the cost to go. So Ui of t is the cost to go starting from time t, which is the minimum over all the policies, alpha, of the cost to go from little t to capital T plus the terminal cost, given the state is equal to I. So that's the cost to go from state I up to t. And by backwards induction, we can get that if we know the cost to go from some time t, then we go to a little bit earlier than that to look at time t minus h, and we can see that that difference is equal to the holding cost that we have to pay starting in state I, plus there's a minimum here. We have to look at so A is the amount of control we want to apply. So we look at how much more costly it is in the other state. And in the case when the other state is less costly, then this difference in here is negative. And then we want to choose A strictly positive and take advantage of the fact that the other state, 1 minus I, has a smaller cost than state I, plus a squared over 2. When you take the derivative with respect to A here, you find that A is equal to the difference. So if the other state is less expensive to go, so U of I minus U of the other state, 1 minus I, if that's positive, then you square that over 2, that's in here, and that's the value of this minimum. And the cost and the control that does that is exactly the difference in the cost. Okay, so the more advantageous it would be to be in the other state, given the current time, the greater effort you would move to switch. If the other state is more cost, let's see, if the other state has a higher cost, so this in here is negative, then you wouldn't want to move at all, and then your control would be 0, and you'll just be happy to stay in the state that you're in. Okay, so that's that. So in summary, if you're given the holding costs and a terminal cost, you can pretty easily figure out the optimal policy for a given player by backwards induction. So just to show that this is really concrete, if we specialize to one player, we could have, say, 0 cost to be in state 0. That would be a nice state to be in, and a positive cost per unit time to be in state 1. So state 1 is one that a player would like to leave. Also, no terminal cost. So the cost to go in state 0 is 0 because the player can just stay there. And I'm going to let y of t be the cost to go from state 1. Okay, so if the player's in state 1, the player would have the option just to stay there and not use the control at all, but then the cost would be capital T times delta. Okay, and if capital T is really large, it would pay for the player to spend some effort to get to state 0. So those Hamilton-Jacobi-Bellman equations where I set y to be the cost U1 of t, and more generally, y is going to be U1 of t minus U0 of t. So y is how much more expensive it is to be in state 1. Then y satisfies this differential equation, which is easily solved. And y looks like that. So this is t's down here. So as you get closer to the capital T, it's not worth, there's no difference between the 2 states because there's no terminal cost. It's just a running cost. But as you back away from T, the difference in the cost increases. And the limit, if you set y dot equal to 0 and solve for y, you can see that as you back away for a long time, the limiting cost is square root of 2 delta. Okay. So if T is really large, on average, the player is going to spend some time in state 1. In fact, 1 over, since this is the limiting difference in cost, and the rate that the player tries to move is equal to the difference in cost, then the player will try to move from state 1 to state 0 at rate square root of 2 delta, and on the average stay in state 1 for time 1 over square root of 2 delta. So if we look at the infinite horizon limit and account for the cost, there's a 1 over square root of 2 delta is how long the player on average spends the undesirable state. And while doing that, the player has to pay delta per unit time because it's not a good state, plus the square of the rate squared over 2, which comes out to square root of 2 delta. There's one other example I have on these slides, and I think with the time lost, I probably won't go in great detail, but this is a case where the costs are the same for the 2 states, but there's a terminal cost in state 1, psi 1, which is 1 over epsilon. So the process does not want to end in state 1 to have this, like if 1 over epsilon is 10, the cost would be 10. So then the cost to go goes up like that. So if you find yourself in the bad state right before the terminal cost, you're probably going to have to pay the 1 over epsilon. But if you have a lot of time to move before the end, then the cost to go decreases like that. So you can find this very explicitly. If you back away by 2 epsilon here, the cost to go cuts in half. And there's some calculation here. This is the cost to go from T0 to the final cost. So for example, if you back off by 2 epsilon, then you have a chance 1/4 of staying in the bad state. If you're in the bad state time T0, you have a 1/4 chance to stay there. And the total cost that you're going to spend is 1 over 2 epsilon. About half of the cost is spent on the rate to try to move to the good state, and the other half is spent on the probability that you don't make the transition. Okay, so you don't want to spend an infinite amount to get to the good state, because if you end in the bad state, it's only a finite cost. It's 1 over epsilon. On the other hand, it's worth trying to move. Okay. So these examples just illustrate how you can do very explicit calculations if they're just a single player, and things should make sense. Things are pretty intuitive. All right, so I want to make a transition now from 1 player to a large number of players. Let's say n+1 players. Say n+1, there might be 100 players, so n would be 99. But there's a total of 100 players, and then we can focus on one of the reference players. So any of the players would look like the single player that we had before. And each player has a control, we'll call it again alpha t. And also there's going to be eta here. We'll assume that there's some positive background switching. So even if the player turns off the jump rate, there'll be some chance to move from 0 to 1. If eta is equal to 0, we're back to the previous case. Then if all the other n players are using the same policy, and it's a Markov policy, so when there's only 1 player, there's no loss of optimality to use a Markov policy, where the rate that you use just depends on your own state. When there's multiple players, it's a real restriction to use Markov policies, because you eliminate things like tit-for-tat punishment, where if some player doesn't behave, then you punish them, and you can get lots of different solutions for infinite repeated games. So we'll just stick with Markov policies. So if the other n players are all using the same policy, beta, then as far as the reference player is concerned, the reference player is only concerned with the fraction of the other players, or the number of the other players in state 0 and the number of other players in state 1. So we can have a reference player like this red player here. There might be 9 players in state 0, 5 in state 1. The players are moving back and forth using some policy, depending on how many are in each side, and the reference player is. And so the n+1 player system with Markov controls is modeled by a Markov process with 2 times n+1 states. Okay, so mean field game theory looks at this situation and looks for a Nash equilibrium in the Markov strategies, and then tries to explain or understand what's going to happen when capital N goes to infinity. And especially Peter Keynes and his coworkers have worked on many applications of this, to a lot of them for wireless access with large numbers of transmitters, for example. Okay, so this is sort of going through the what a single player does. If the state is I, then the player makes a transition to the other state with probability alpha t plus eta. So alpha t plus eta now is the transition rate. The objective for the reference player is to minimize a similar cost. This is the same as before as for a single player, except now there's this theta t here, where theta t is the fraction of the other players in state 0 at time t. So the players are coupled only through the cost function. Each player has the same cost for, well, it could depend on theta, but usually I'll look at a case like this where we have fi theta alpha squared over 2. So before with one player, there wasn't a theta here. Okay, so that's the only difference, is that the desirability of a given state may depend on the fraction of other players that are in that state. And a nice example to think about is the follow the crowd example, where we have this function. So if we follow the crowd, the players like to be in the same state. So if theta is the fraction of players in state 0, if that's equal to 1, then the cost for being in state 1 is high, it's 1, and the cost for being in state 0 is 0 because you're with all the other players. So the undesirability of a state increases linearly with the fraction of players that are in the other state. Okay, so the title of this talk is about non-uniqueness in mean field games, and you could already see if you started like half the players on one side, half on the other, they might like to like all converge, convene in state 0 or convene in state 1. And so there could be possible non-uniqueness of some equations that I didn't even talk about yet. Okay, next I'm going to talk about the mean field game equations. Well, actually, first for the n+1 player game, if you think about this, you could have all players, even if you don't have the symmetry property, have every single player decide what control they want as a function of theta. And there are Hamilton-Jacobi-Bellman equations for the n+1 player system. And to save time, you can look at the paper. Paper is on archive. I'm not showing the Hamilton-Jacobi-Bellman equations for all n+1 players, but there's a couple interpretations of that. So if the other n players are choosing some policy beta, then the equations determine the optimal policy for the reference player. Okay, so the reference player is interacting with a Markov process because all the other n players, if they fix their policies, their Markov policies, to the reference player, it looks like a pretty complicated Markov control problem with 2 times n+1 states, or even 2 to the n states, because it could be asymmetric in the other players. That's fine. Whatever the other players do, there's an optimal policy for the nth player. And then, but all the players should be optimal, and it turns out there's a unique solution to the Markov perfect equilibrium for n+1 players, and it's a symmetric. Since there's only one solution, it has to be the symmetric one. So you get a unique Markov perfect equilibrium out of this. Okay, so mean field game theory may be interested to find out how does this behave when you let n go to infinity. Okay, I'll talk now about what mean field game equations are. So we can go back to a single reference player. So suppose theta t, instead of being determined by n other players that are randomly moving, it's just a deterministic trajectory. Just deterministic. Then we're back into the case of a single player, where the theta of t is really part of this f. And then there's the problem I talked about with the single player, and we have the control, and there's a solution for the reference player. And then if the reference player, which is in terms of the cost to go for the reference player. So if the cost to go function is u, then u1 minus u0 positive part, that's the rate that the reference player wants to use to move. And then if all the players apply that same policy, then that determines evolution. And if you have the law of large numbers, you have a large number of players, that determines the evolution of the mass trajectory of the fraction of players that are in state 0 and in state 1. That comes from the Kolmogorov-Ford equation. The same one, that's for a single player, that would give you the probability of being in state 0 or in state 1 at time t. But with a very large number of players, and by the law of large numbers, that'll give you the fraction of players in state 0 or state 1. So the mean field game Nash equilibria are the fixed points of a mapping T, where we take some trajectory that represents the fraction of players in state 0 as a function of time. That maps to a cost to go function for a single reference player. And we assume all the players react to that same theta in the same way. And then we look at the Kolmogorov-Ford equations to come up with theta tilde, which is a fraction of players when they're using those controls that are in state 0 or state 1. And if you have a fixed point for this equation, then that's what mean field Nash equilibria are. Maybe this is a good time to pause. Siva, did you want to ask any questions or?
I don't see any questions on chat. I don't have any questions, so I'm good. So we're taking a short 1 or 2 minute break. If anyone has a questions, this is a perfect time to ask.
Hey, this is Stella from Georgia Tech. I have a question regarding the uniqueness, existence and uniqueness of equilibria. I might have missed that part. I was just wondering, how do you justify that at least one or exactly one exists?
Okay, this is for the finite system. So the system with n+1 players, I didn't write the equations down, but they're ordinary differential equation with 2 times n+1 dimensions, or you could even have 2 to the n dimensions if you go to the full view where every player can follow. And so it's just working backwards by induction. It's a special case that we're working in continuous time. If you look at Markov perfect equilibrium in discrete time, when there's like 5 steps to go, then you want to figure out, you know, what the players are going to do when there's 6 steps to go, and then they all play a little game, like a stage game at each stage. But in continuous time, those stage games reduce down to nothing, and the players follow equations very similar to these Hamilton-Jacobi-Bellman equations.
Mm-hmm.
So basically, the rate that each player wants to move is proportional to how much better the other state is going forward. But you solve the Hamilton-Jacobi-Bellman equations for the n+1 players simultaneously working backwards from the end. And there's only one solution.
I see.
It's also, when you're solving the HJB equations, you're solving them simultaneously for all the states that you're in. Because so for amount to go of time t, you solve cost to go for each I. Whereas when when we look at the, there's some echo here. When we look at the mean field game equations, we start out with some trajectory theta that starts out with some initial point. Okay. So for the n+1 players backwards programming, we don't have an initial state. I mean, we're solving it for all possible states as we go backwards from the end of time. And then once you've solved those, then if someone gives you an initial state, you just plug in those, you use those U's that give you the control.
Okay, so it's basically because of the uniqueness of solution of the Hamilton-Jacobi domain that describes the mean field game.
Yes. Well, it's not the mean field game. This is for n+1 players.
Right.
There is non-uniqueness of the mean field game equations. This fixed point here. But there is uniqueness for the finite number of players, but
okay.
Actually, I'm going to try to go back to my iPad because it seemed to be working now again. Oh, maybe that's, let's see, am I screen sharing? I think I have to go to my midnight desktop again. Okay, can you see this?
Yes.
Okay. All right, so so I'm going to specialize to the follow the crowd cost function for the n players. So for follow the crowd, this is, I talked about this before. The cost, the holding cost to being in state I is given by this. So if I is equal to 0, then it's 1 minus the fraction of players that are in state 0. So if all the players are in state 0, then the holding cost of state 0 is 0, and the holding cost of state 1 is 1. Okay. So if we look at the mean field game equations, so we're looking now for a single player, and so the single player, well, these are the Hamilton-Jacobi equations. I mean, and then this is the Kolmogorov-Ford equation. We get these coupled equations, and you can actually reduce this further by letting y be the difference in the cost of state 1, state 0. So I'm just going to call that y, and then we don't need to have quite so many equations. So, okay, in the case theta bar is equal to half is interesting because one solution is theta identically equal to a half. That means half the players are in state 0, half the players are in state 1, and then U1 of t and U0 t are 0. It'd be 0, 0. The two states are the same, and the players just stay where they are. Okay, but if there's a large number of players and there's a large time horizon, like if there's 1,000 players on each side, 2,000 players total, if one of them moves to the other side, there'll be 1,001 players there and only 999 on the first side, and it'll be a little bit better. So they should all spend a little bit of effort to move. And then once you have 1,001 players on one side, then that state becomes more attractive, and you get more and more players moving to that side. So you can see that with high probability, you're either going to have, with probably 1/2, all the players trying to go to one side, or all the players trying to go to the other side. Okay. And that's reflected in having multiple solutions to the mean field game equations. So if we let x be 2 theta minus 1. Yeah.
Sorry for interrupting. Can you make it full screen so that the whole slide is visible?
Oh, yeah.
Thanks.
Right, okay. So x is 2 theta minus 1. So theta is the fraction of players on state 0. So x goes from -1 to 1. So if x is closer to 1, that means more players are in state 1, and it's state 0. And when x goes to -1, they're in state 1. And then y, as before, is the difference in the cost between the two states. And these two together, the mean field equations just reduced to a 2-dimensional equation. And these fall into a special case that the dynamics of this is a Hamiltonian dynamics. So it's pretty easy to get a picture of what's going on here, because this has the form of x dot equals a partial of h with respect to y, and y dot equals minus the partial of h with respect to x, where h is this function here. Okay. If this eta, remember eta is the background jumping rate. If that's equal to 0, and if x and y are small, this is really dominated by x squared plus y squared over 2. It looks kind of like a parabola going up. And the thing about Hamiltonian dynamics is the value of the Hamiltonian stays constant. So if you just plot the Hamiltonian function, you can see what's going on with the dynamics pretty easily. So here's a contour map of h when eta equals 0. And we have a 2-dimensional ordinary differential equation. There's one terminal condition and one initial condition. So that's kind of the difference that the mean field game has with the n+1 player game. There we only had conditions on one side, the terminal condition, and we could work back and have a unique solution. But here we have an initial condition. The initial condition is what fraction of the players are in each state. So if x is equal to 0, for example, that corresponds to half the players being in state 0 and half of them being in state 1. And then the final condition is y equals 0. Y is the difference between the cost of being in state 1 and the cost of being in state 0. So we have to look for a solution that starts on the vertical axis and ends up on the horizontal axis. Okay, and for eta equals 0, there's one solution that's like this. Now, by studying this Hamiltonian, you can see that the closer you start in towards 0, the faster it can move around. And actually, if you start out with x and y being very small, this cubic term doesn't matter very much. And you can just see how long it takes to go around here. And so if t is small enough, there wouldn't be enough time to go on this trajectory. And the only solution is just to stay at 0. Staying at 0 is always a solution. If t is a bit larger, there's a solution that starts here and comes down there. If t is larger still, we could start up higher, loop around, come over to there. Or if it's larger still, we could start up higher, go around like that. So as t increases, we get more and more solutions. That's reflected in here. So these are the theta value. So I switched back to the theta instead of x. So if t is less than pi over 2, then there's only one solution. When t exceeds pi over 2, there's two solutions for the theta. One is trying to go more towards state state 0 and the other ones are going towards state 1. If you increase t beyond here, then we have one solution. These are the solutions you would expect. The players are going towards state 0 or they're going towards state 1, but you start getting these oscillatory solutions. So these oscillatory solutions are the players start going towards state 0, but in the future, they're all planning to move to state 1. And since that's what people are planning to do, it's consistent for them to do that. So they start moving towards the other state. So you get these oscillating states. There's no leader here. There's no one trying to influence. In fact, I think an interesting area here would be, what if you have a small fraction of players that are trying to influence the crowd to steer towards one of these equilibria or another? Okay, so we define what's called a fluid limit trajectory, which, and we think for this, we think that if t is less than pi over 2, there's only one solution here, and we think that's the unique fluid limit trajectory. When t gets bigger, when now we have 3 solutions, we think the one in the middle is no longer a fluid limit trajectory. In other words, the crowd is either going to follow the upper trajectory or the bottom trajectory, but it won't follow that middle one. And then when we get more solutions, like here, there's 5 solutions, we think only the top one and the bottom one are fluid limit trajectories. And the definition of fluid limit trajectory, which we have in our paper, is that as you let n go to infinity, there's a sequence of initial probability distributions, so that if you start in that initial probability distribution for the occupancy of the states, then the mean field game population will follow that trajectory. I talked about before, if you start exactly with half in one state, half in the other state, then even when the large number of players goes to infinity, the population trajectory will be random, because half of them will probably one half will go to state 0, probably one half will go to state 1. But if you start with a square root of n of the players in state 0, let n go to infinity, then they'll all end up in state 0. So you end up with a deterministic limit. Or if you change the initial condition a little bit to let them all start in state 1, then deterministically the population will follow that trajectory. Okay, so even all these oscillatory ones, the fact that they're fixed points of that mapping implies that they're ϵ-Nash strategy profiles. That means if everyone follows those strategies, then a given player following that strategy will only be giving up some epsilon with respect to the optimal response, where epsilon can go to 0 as n goes to infinity. So there are a large number of solutions, and for this problem, we've characterized, these are all the solutions of the mean field game equations for this, and they're all ϵ-Nash strategy profiles. But do the mean field game equilibria have do some of them have a stronger property? And that's the definition I talked about before, the definition of a fluid limit Markov perfect trajectory. So we say that a theta is a fluid limit Markov trajectory if for some sequence of initial states with the fraction starting in state 0 converging to theta 0, when we look at if we look at the finite system, so you start the finite system where there's a unique solution to the cost to go functions. There's a unique, once you set the initial condition for the finite system, it's a unique stochastic process. And so the idea is that you can find a sequence of initial conditions as n goes to infinity so that the finite system with large n, the fraction that are in state 0 follows the state of t within some epsilon, where for any epsilon bigger than 0 over the whole period. So it's like a formal definition of fluid limit Markov trajectory. And the proof, the only result we have in our paper is that if a trajectory is a fluid limit Markov trajectory, then it is a solution of the mean field gains. Okay, so if you want to find fluid limit Markov trajectories, you could limit your search to the solutions of the mean field gain equations. Okay, and the proof of this uses a Gurzanov type change of measure argument, and it's well beyond the scope of this lecture, but I could say what's the main idea here. So so suppose you have a fluid limit trajectory. That means you've got some theta, and if by choosing the sequence of initial conditions, you can get the large n system to follow that theta. Why is that a mean field? Why does that trajectory have to be a mean field gain Nash equilibrium? Okay, so the idea is if a player, let's see, well, it's kind of complicated. Basically, you have to look at the n+1 player system, and if that's following some trajectory, if one of the players changes strategy, then the idea is that doesn't change the mass population very much. Okay, and that's because if one player changes strategy, that essentially it's equivalent to a change of measure where the likelihood ratio between the two measures is nearly bounded. It's not bounded, but it's with high probability it's not too large. So this event here has probability converging to 1 under an original measure. If you change the measure and the likelihood ratio is not too large, then the probability of the same event under the other measure has to also converge to 1. That's an idea here. Okay, so now we know that we can look at all the mean field gain solutions and ask which ones of those are fluid limits. Okay, so these are the trajectories we think are the fluid limit trajectories. These are simulations. So we do a simulation with 400 players, with 200 players in each state, and we never see the finite system oscillating. They all go to here. And also beyond pi/2, they don't stay at the straight line here. So conjecture, this open problem, is that the fluid limit Markov trajectories are the stable fixed points of the mean field gain mapping. And we're able to show that this solution right here is stable for t up to pi/2, and then it becomes unstable later. Here's some numerical things where we iterate. This is what we think is unstable. We do a slight perturbation, keep running, iterating numerically, and we find it converges to one of these other trajectories. But we can also we can linearize, and the Gateau derivatives of this operator that we're trying to find fixed points for, the derivative is an integral operator, and this k here as a form of a covariance matrix of a Brownian motion, and we can calculate the eigenvalues explicitly, and this first largest eigenvalue crosses 1 when t gets bigger than pi over 2. So the mean field fixed point mapping goes unstable exactly when t crosses pi over 2. And if things are not so symmetric, it's not so obvious where the borderline is and which trajectories you're going to follow. So, and there's lots of interesting connections coming up in the recent literature. Kavita has a couple of her students worked on this. There's very promising work on using partial differential equations. I think the non-uniqueness of the mean field game equation is also related to non-uniqueness of solutions of associated PDEs. A PDE is trying to take a limit of the Hamilton-Jacobi-Bellman equations for the finite n+1 system and sort of turning it into a partial differential equation where a difference of one player or not turns into a derivative with respect to space, or the derivative with respect to the number of players. I think I'll end there. If there's any questions, but we have a paper in archive under Hajek and LiveSay. Thank you.
I have question answer session now. I'll start with a question. So Bruce, you mentioned that if t is greater than pi over 2, the flat line where everybody is where half the agents are in 0 and half the agents are in 1,
right,
does not continue to be a equilibrium. So intuitively, why is that? So if I look at a sequence of systems where exactly half start at 0 and exactly half start at 1 without any square root of n perturbation, then shouldn't I expect that that will continue to be the equilibrium?
Well, it takes some effort to move, okay? And if the other side is not attractive enough, they're not going to expend the effort. And if the horizon is kind of short, it's not worthwhile to position themselves, to get together. But with a longer time horizon, then there's some benefit to spend the cost to get together because it's over a longer period of time.
I see. Got it. Thanks.
So, so the longer, so if there's 3.5 time units to go, you're going to you work pretty hard because you've got a pretty long horizon. And if you look at all the solutions, the ones that go straight up, they start going up faster and faster.
Thanks.
Yeah.
Hi, Bruce. I have one question. Can you go to slide 20? Yes, thanks. So regarding the picture, the second row, the paths can be seen to arrive at the same point and then again diverge, right? So what is causing that in the middle? Yes.
Well, there's some symmetry between 0 and 1, so they just happen to cross.
So at that intersection point, all of them have the exact same fractions, like same state, or is there any change? Different states?
Remember, this is one variable of a two-dimensional ODE. Okay, so at this point, this population was going towards state 0, and in the future they're going towards state 1. So that's why they start going down there.
Mm-hmm. Thanks.
So yeah, it's a two-dimensional state. I mean, they're just following that OD, so they're just following along like this. So you could have one trajectory. I think some of these correspond to trajectory going that way. Let me go, like say going around here, and the other one's a trajectory just going the other way. So you can make a quarter turn or 3/4, and the other one goes here, and at some point they're going to have to pass up, be at the same place, but they're going in different directions on this contour.
Hi, Bruce. This is
Yes.
Vijay. I have a quick question. This is even for the finite player game. If if you have an infinite horizon problem, are you guaranteed to have an equilibrium? And what happens if you look at the mean field game as the time horizon is infinite from the beginning?
For this problem, you have an equilibrium. Yeah, so you can be looking at the cost per unit time in steady state. And
Yes.
actually the Sean Mine paper, that's what they looked at, is sort of the infinite horizon. There, it's kind of hard to write down the transient case. I think this is the simplest setting where we can actually talk about the transient problem, and then you can get the infinite horizon as a limit, and you can understand the infinite horizon as a limit. Whereas in some other context, you can only explicitly do anything about the steady state.
Mm-hmm. Well, thank you.
Hi, Bruce. This is Lei. Can you go to slide 20? Yeah, so for all these equilibria, are we assuming they all start from initial condition theta equal to half?
Yes.
Okay. So how about like if they start from other initial conditions?
Very similar.
Very similar when they converge to half, or will they stay where they are?
Well, okay. So if we started somewhere else, so you start out with half of them in 0.6, then it would go up a little bit. We'd only have one solution. I think there's only going to be one Markov fluid trajectory that I talked about, but still you're going to have oscillating solutions. So you'd have, and you can figure that out by starting wherever you want on this picture. So I happen to choose cases where x starts at 0. So x is 2 theta minus 1. So x equals 0 is like half and half, but you could start somewhere here. And then you'd have just one solution here, but then when the horizon got larger, you used to have multiple solutions where you keep going around this multiple times.
I see. Thank you.
Yeah.
Hi, I have yet another question about the funky equilibria. So you mentioned when responding to an earlier question, I think Deb on course, that that basically note that the sort of strange oscillating equilibria are because there's this second variable that's not shown in that plot.
Yes.
Which is that, so is Y roughly speaking playing like a momentum role here?
Yeah, I think you could think of it that way.
And then sort of following up on that.
Yeah, because when you have Hamiltonian dynamics, often this you've got a state and a momentum. Yeah.
Mm-hmm.
Yeah.
So then maybe related to that, it's you explained earlier the intuition for why the constant solution is stable up until a certain time horizon.
Yeah.
And it seems like the oscillating solutions aren't stable. Is there an intuitive explanation for why those ones aren't stable?
No, I've just made a conjecture that it seems kind of precarious where everyone has in their notes somehow that they're planned to follow this oscillatory thing, but it's like people following the rules for COVID-19. Some people stop following, and then other people say, "Hey, I don't need to follow this either," and they drift away from it. But I really don't have. I mean, in the simulations I showed, it just didn't seem to happen with the finite n system. I mean, there's nothing built into the equations for n+1 that have this oscillatory behavior in it.
Okay, cool. Thanks.
It just doesn't come up. There's, if you really want to get into this, there is a lot of very interesting work in the last year on, the last maybe 4 years on a partial differential equation approach. These, if you know, they are hyperbolic differential equations with order 1. So you have the partial with respect to t of something is equal to the partial of x of something. And you can view that as the directional derivative is equal to 0 in a certain direction in space-time. And these mean field game solutions, they're called characteristic curves. They're the characteristic curves of these partial differential equations. But the partial differential equations themselves have to be defined everywhere. So that's something to look at.
Hi, Bruce.
Hi.
So for this follow the crowd game, it is a case where different players are only coupled through the cost function.
Yeah.
So do you have any comments for how one would deal with the case where they're also coupled through the actions, like the action space for a player is constrained, the constraint for one player's action depends on other people's actions?
No, I don't. That can get pretty complicated. And again, this is also somewhat artificial in the sense that we're looking at Markov perfect equilibrium. So we rule out behavior where they could take actions depending on the past actions and have like punishment strategies and so forth.
Okay, yeah, thanks.
Isaac, did you have a question?
Yeah, I have another follow-up question, if I can.
Can you hear me?
Bruce, is Vijay here again. So in terms of your conjecture with the fluid solutions, even if that is true, is there an alternate characterization that allows you to determine them easily? So because if you think that's where the system is going to converge to, those are the only equilibria we should study.
Right. I mean, one way to find fluid limit trajectories is just simulate the n+1 player game, and like here.
Yeah.
So it's a question: is there some numerical way that doesn't use simulation that could identify the fluid limit trajectories? And so the result we have narrows it down to the solutions, the mean field game. So we're limited in this case down to like a finite number of choices. And then if we could, numerically test the stability, or in one case, just in one case, we can linearize. We have a integral linear operator for the derivative, and we can do the eigenvalue expansion, and we can see that the largest eigenvalue crosses 1 at this critical point. So that's kind of entirely without doing simulations. But doing that numerically for examples like this, the integral operators get quite complicated. I think it could be done numerically. I think it's still going to be an integral operator, but given some kernel for an integral operator and seeing whether it's stable or not requires, you could discretize it and do a spectral, decomposition of a matrix to find the eigenvalues.
Hi.
Thank you.
Is my microphone working now?
Hello?
Hi, can you hear me now?
Yes.
Okay, I was wondering, so when we define the fluid limit game, we allow sort of a perturbation that vanishes in the mean field limit in order to get these equilibrium, but we only have those at the initial condition.
Right.
What if we allowed those vanishingly small perturbations like anywhere in the time period? Would that give us more trajectories?
I don't think so, but I don't know for sure.
Okay, in particular, I was wondering like if you could start along the central line and then have the perturbation maybe halfway through. Like if you
Yeah, but I don't think the mean field, the finite game is going to follow that.
it won't follow the central line in the first place.
It wouldn't follow the central line in the first place if you're beyond pi over 2.
Okay, and once you've started diverging away from the central line, the perturbations don't really matter anymore.
Yeah. So I think even a small perturbation in here is not going to keep it from staying on that line. I think it would perturb it and just sort of stay along there.
Okay.
It still wouldn't be worth it for them to start moving.
Okay, so the initial condition is really the only place that matters.
Well, that's what we think. You could have considerably more complicated situations, so it's
fair.
It's possible that you want to do perturbations elsewhere.
Okay, thanks.
Maybe that's part of the conjecture, is it doesn't need to be fixed up. There's something called in PDEs, there's something called entropy solution, which has kind of a similar stability property as it might sound from the name entropy, and that predates this mean field game theory. So there actually is a concept called entropy solution for hyperbolic differential equations.
Bruce, I have another question.
Yeah.
Can you go on to slide 14?
14.
So this is for the n+1 player game. So I was just wondering where n shows up in these equations.
It doesn't. This is for the mean field game. There is no n.
Oh, I see.
So theta is a deterministic function, and it represents the population. And so if that's the population, that's how people are going to go, then every individual has a response to that, as if it was a single player. And that will, depending on the initial condition of the player, by the Kolmogorov equations, it will say what's the probability that player is a state 0 or state 1 at any point in time. And then assuming all the players act the same way, then you get a theta. So that's where you get this fixed point. We start out with theta, optimal response to that, giving you a new theta. If that's a fixed point, then it's like self-consistent. So it's like somebody publishes in some book to the whole population, said, this is how we're going to act. It has to be a fixed point, or else it's not consistent for them to act that way. But if it's a fixed point, it's kind of consistent. And if they have a chance to deviate, they won't, because they say, well, that's what everybody else is doing.
So towards the end, you showed the simulation for this 400-person game, but you hadn't shown us the equations corresponding to that, right? So that's what I was trying to clarify.
What do you mean the equations? It's just a simulation. So, okay. So they, yeah, so I didn't show the Hamilton-Jacobi-Bellman equations for n+1 players.
Okay, got it. Thanks.
It's the same principle as for one player, where you recursively going backwards from the end of time, seeing what the cost to go is for each player from each of the two states, and then they choose a rate which is proportional to the difference, if it's in the right direction.
Okay.
And you just work backwards.
Okay.
Yeah.
Thanks. So we'll stop the recording now, and we'll also stop the live streaming. So we'll officially end the talk, but you're welcome to hang out for a bit if you want to chat with Bruce or with others and so on. So let's all unmute ourselves and then thank Bruce again.
All right, thank you very much.